Video, I wanted to go over our next project, which is optimization and simulated annealing. So first off, what is optimization? Well, it's pretty simple. All optimization is it tries to find the maxima or minima of a given function. And this actually has a lot of real-world practicality to it. In many instances within industry or scientific research, you're going to have multiple parameters that feed into some sort of function that determines your profitability or effectiveness or whatever. And we want to figure out how to tune those parameters such that maybe we can get the maximum amount of profit or the minimum amount of materials or labor used. And optimization gives us an algorithmic way of taking one of these functions and actually finding the maxima or minima. And within this project, we're just going to be looking at minima. And in order to do and calculate this minima, we're going to use something called the gradient descent method. And this descent method actually can work on functions of multivariables. But I first want to go over a one variable scenario, and let's go over it qualitatively so we can understand what this method is actually doing. And so all this method does is we start at some point just randomly on the function, and we're just going to look at which way is down. So which way is down is determined by the slope. And so we can calculate the slope at that point, and then we look at which way is down, and we move slightly in the direction of down. So if we start here, we take the slope and we notice that down is this way, so we move slightly in the direction of down. And then we look at that point again. We look at the slope and we go slightly in the direction of down. And we keep doing this until eventually we find the slope to be 0. And we know that if we have a slope of 0, we've reached either a maxima or a minima. And so if we keep going down, we know that we've reached a minima. And so that's all the gradient descent method is. All we're doing is we're looking at the slope and moving slightly in the direction of down until we reach that minima. But as I said earlier, gradient descent can actually be applied to multivariable functions. And we do this by taking a derivative in multivariables, and that is called gradient. And so I actually have a function over here in order to demonstrate what the gradient is. And so as you can see here, this function has two variables in it, x and y. So you can see it here. And when we're trying to take a multidimensional derivative, it turns out we can only take the derivative with respect to one variable at a time. So we actually break down taking the gradient into two separate parts. We can first take f of x, which is a partial derivative with respect to x, and then the partial derivative with respect to y. And then we can combine these to actually become the full-up gradient. So if I was to take f sub x, what you end up doing is you only pay attention to x. So x is the only variable you care about, and any other variables within the equation become constants. We just ignore them. So if we were to take s of x, we look at this first term, and we know how to take this from regular calculus. That just becomes 2. And then as you can see here in this term, it has y. And well, we're treating any other variable besides x as a constant. So that just goes to 0. So f sub x is 2. And now for the partial derivative with respect to y, it's the other way around. We're only paying attention to y, and x is now just a constant. So this first term goes away because it's just a constant. And then we know how to take this derivative from regular calculus. That just turns out to be 8y. So we can combine s of x and s of y into this gradient. And so if we have a multivariable function, we can take this gradient, which again gives us this idea of down, and we can continue to move in this direction of down until eventually we reach a minima. And so the gradient descent method actually goes over that. What we do is we take the gradient of our function at our starting point, we look to figure out which way is down and move slightly in the direction of down. And we keep repeating that step until we eventually reach a gradient of 0. And what is a gradient of 0, right? How do we find a zero-dimensional slope if there's multiple partial derivatives, right? And well, we can find that by taking the norm of a gradient. And that's just a way of summing up all the parts of the gradient. It's taking each element of the gradient, squaring it, adding all those elements together, and then taking the square root of that sum. So once we get a norm of 0, we've known that we've actually found the minima in that multivariable function. And so, again, I would just want to stress that the process is no different from working with a single function. All we're doing is we're finding the gradient, which is the fancy word for slope. We're finding which way takes us down on that gradient, so we subtract a small part off, we keep looking down, and then we keep repeating this step until eventually we reach a minima of the function. It's no different. And so that's gradient descent. But I would like to point out that there is a lacking quality to gradient descent. Imagine here if we wanted to find the global minima of the function. And again, the global minima is going to have a lot of practicality too in real-world scenarios. Sometimes it's best to find the lowest point on your function. Well, if we were doing our normal gradient descent method, we're not guaranteed to actually find this global minima. Imagine if I started here, right? Well, if I took the slope and kept moving downwards, I would eventually hit this minima. I will never see the global minima of the function if I'm doing standard gradient descent. And that's an issue. And so simulated annealing helps give us a way in order to find the global minima with a high probability. And it actually relies on an element of randomness. And so this randomness element actually allows us to jump across the equation to different parts of it, and with a high probability we'll actually end up centering on the global minima. So I'm just going to go over a qualitative version of simulated annealing just to try and explain it to you guys. So if we start off here, what we do is we keep jumping around the equation. And as we jump around, we start to jump around less and less. So as more iterations go on, we jump around less and less and less. And as we jump around less and less and less, gradient descent starts to take over. So then once we've jumped around a bunch of times, then we just do standard gradient descent. And so if we've jumped around a bunch of times, we'll eventually hit somewhere around our global minima, and then we can perform gradient descent like normal. And so it's a little bit of a confusing algorithm, and to be honest, I'm confused by it too. It's odd that it uses randomness in order to jump around and somehow with a high probability actually end up getting this minima. But I'd like to point out that since this week's project is harder than these first three, we've actually provided a lot of the pseudocode within the project documentation for you. So do read it over, and you can translate it into actual MATLAB code. And so you don't have to worry about completely understanding what simulated annealing, the actual intricacies of it, but if you're able to translate that pseudocode, you'll be able to successfully complete this project. So I hope this video has helped, and again, if you guys need any help, just come talk to me during office hours or text me, and we'll be able to figure it out. Thanks.